sphere. The celestial sphere is the imaginary crystalline sphere on which all of the stars exist. The Earth is the center of the celestial sphere. So we get this idea back from the Greek times when they actually used to think that stars are on a crystal sphere. Okay? But of course now we know that that's not true. So imagine here you are the Earth and you're trying to plot where the stars are. What is their location? How can I find stars? Well, in order to plot stars, in order to know how to see them, I don't really need to know how far they are from us, right? If a star is here, does it really matter to me if it's close or far? If a star is there, does it matter if it's close or far? No. As long as you tell me where the star is, how to find it, I don't need to know how far away it is. So what we do is, stars, no matter how distant, they are pictured as being on a single crystal sphere. So bring them down, and then now state where are they located on that sphere, you see? So even though the concept of a sphere, a crystal sphere is not true, as a scientific model, it's still a helpful model to write down where stars are in the sky and how they travel in the sky. So it's a good scientific model. Okay? And then we're going to talk about what the horizon is, the human experience of the celestial sphere. Our horizon, our zenith, is the point above us. Okay, so we'll exit this out. Okay, so then just like we do on Earth, we take the celestial sphere and we break up into different marks, into different lines. We take the celestial sphere and we break it up into half. That's called the celestial equator. This is the line that separates the celestial sphere into a northern and a southern part. It lies right above the Earth's equator. So if you're on the Earth's equator, you look straight up, you should be seeing the celestial equator. That the celestial equator cuts the celestial sphere in half. You see? The celestial North Pole, of course, would lie right above the Earth's North Pole. If you live on the Earth's North Pole, you look straight up, you would see the celestial North Pole. It is the point about which the celestial sphere rotates. Okay? It rotates around the Earth's North Pole. Why does the celestial sphere rotate around the celestial North Pole? Because the Earth rotates like this, right? So the Earth rotates so the Earth is like this. The Earth is rotating like that, right? So of course, when we look at the sky, we think we are stationary and the sky is rotating. That's the reason why the sun rises every day and sets every day, right? The sun rises and sets, sun rises. Is it actually rising and setting? No, we're the ones that are rotating in 24 hours time, right? And then it appears to us as if the sun is rising and setting, rising and setting. Well, the same reason for that, the Earth is spinning around like this, around the axis. And then to us, this is the North Celestial Pole. So we think we are stationary, and then the stars are rotating around the North Celestial Pole like that. Like that, like that, like that. So whatever star is nearest the North Celestial Pole will never rotate, or very minimal rotation. That star happens to be Polaris. Okay? It's our North Star. The celestial South Pole lies right above the Earth's South Pole. So if you live on the Earth's South Pole and you look up, of course this looks like you're looking down, but of course you don't look down when you live there, you still look up. You look up and you see the South Celestial Pole. Okay? The ecliptic. The ecliptic is the projection of the path of the sun on the celestial sphere. Okay? So let's erase this for a sec. There's a couple different ways we can visualize the ecliptic. So you see what this one is showing here as the Earth is going around the sun. In June, when we look at the sun appears to be in the constellation Taurus, you see? And in August, when we look at the sun appears to be in the constellation Cancer. Of course, the sun is not doing anything, right? It's just standing there. But we're going around the sun, you see? So we go October, sun appears to be in the constellation Virgo. So as we are going around the sun is stationary, whichever constellation the sun is in, so the sun is traveling a path across the celestial sphere. Okay? That is known as the ecliptic. See? Ecliptic, sun's path. Over here, the ecliptic looks like it's going to be a straight line, right? But in a second, you're going to see that it's not a straight line. It's an arc, but when you draw that on a flat map, it's going to actually be not a straight line. It's going to be a curve. Okay? The ecliptic makes an angle of 23.5 degrees with respect to the celestial equator. Okay? The ecliptic makes an angle of 23.5 degrees with the celestial equator. So what does that mean? Why? Have you heard of the 23.5 degrees? Where does that come from? Anyone? As the Earth goes around the sun, at what angle is the axis of the Earth tilted? Okay, does the Earth go around the sun like this? Let me bring a little better marker here. Here's, let's say, the Earth. And here's the sun. Does the Earth go around the sun like that? Or does the Earth go around the sun like this? Which of the ones is true? The top one or the bottom? Bottom. Okay? When the Earth is going around the sun, the axis of the Earth is tilted, and it's doing this. You see? It's tilted by 23.5. In a couple of lectures ahead, we're going to see that this is why we have seasons. And you'll understand why this causes seasons then. Remember at the beginning of the semester I said the most important lecture I want you to remember is the one on seasons. So that's lecture 4. I want you to understand why we have seasons. But this is also related to the ecliptic, you see. Is there a planet that does this way, that's vertical? Yeah, the most closest planet that does that is Mercury. Mercury. The Mercury doesn't have a tilt at all. Another planet that has a very small tilt is Jupiter. Okay? Jupiter's tilt is like 3 degrees, barely anything. Okay? So therefore, remember the previous picture I drew for you was I drew the Earth and I drew it vertical. Why am I drawing the Earth vertical and then drawing the celestial sphere like this? Because from this picture, I'm trying to imagine what the sky would look like from our perspective. The other picture that I'm drawing with the Earth tilted, that's from the solar system's perspective. So if someone is from the outside looking in, they will say the Earth is tilted. You see? Like that. Now, if I go inside of the Earth and I look at the sky, I'm not the one tilted, the sky is tilted, right? The sun is the one tilted. This is kind of like why everybody thinks they're always correct. because they look at everything from their perspective, right? No one ever says I'm wrong because you view everything from your own perspective. You got to kind of come outside of yourself to view yourself and say, yeah, maybe I was the one wrong there, you know. This is a little life lesson. So from our perspective, we are straight right side up. This is the north celestial pole. This is the south celestial pole. The celestial equator is like that. But of course, it comes back around the other side, right? The celestial equator. What does the ecliptic look like? The ecliptic is when we view the sun, what the path of the sun will look like on the celestial sphere. What is the path going to look like? Like this. The path of the sun is going to look tilted by how many degrees? The same number of degrees as the Earth's axis is tilted when you view the Earth's orbit from the outside. 23.5 degrees. Okay, this angle here, 23.5 degrees. So the sun goes like that. 23.5 degrees. When does the sun approach its highest point in the sky? When does the sun approach its lowest point in the sky? Well, to answer that, we need to know. I'm trying to give you the two views at the same time. This is from the outside solar system. When is the Earth most tilted towards the sun? When does that happen? Beginning of summer. June 21. In other words, we're pointed straight towards the sun on June 21, right? When are we most tilted away from the sun? Beginning of winter. Winter solstice is when? December 21. Or roughly around the 21st, 21 or 22, you know. So that's the winter solstice. And that's why, one of the reasons why Christmas is celebrated on the 25th, because after that, the days get longer, so it has to do with the sun god, and we celebrate the days getting longer, you know. So, the time when the Earth is most tilted towards the sun, so imagine you guys are the sun now, right? I'm going to illustrate this. You are the sun. On June 21, I am pointing down. I'm pointing down by 21. In order to look at you, which way do I have to look? My eye. If I look straight down, I see the ground. In order to look at you, I need to look up. So that means you guys are above my horizon. You see that? By how many degrees? By the same angle that I'm tilted. You see? So the sun approaches the highest point in the sky on June 21. You see? Now this one, I'm tilted away from you, okay? By 23.5, December 21. Now, if I have to look at you, I got to look down. You see that? So, December 21. Okay, how about the middle of those as the Earth goes around? As the Earth approaches here, that's June, this is September 21. September 21, I'm still tilted, but now you're the sun over here, you see? So I'm tilted parallel to you. So in order to look at you, I just look sideways. I don't need to look up, I don't need to look down, you see? So where's the sun on September? It's crossing the celestial sphere, you see? So that's September 21. I made the intersection of the blue line with the black line. You see? Going like that. And then on its way back, March 21. That's here. You see? March 21. So on March 21, the sun crosses the celestial sphere. On September 21, it crosses the celestial sphere. On September 21, the sun is headed downward. You see here? September 21, the sun is headed downward. And then in March 21, the sun is headed upward. This way. Now, you might say, you know, teacher, this picture is a little hard to visualize because it's almost like 3D. Okay? Can you make this 1D? Yeah, we could. Just like any other map, we can take a globe, right? And we can flatten it out and we can draw a flat map of the Earth, right? You could do the same thing with the sky. Flatten out the celestial sphere, and then it'll be flat, and then it will look like this. And this is one of the files that I asked you to print out from my website. So if you printed it out, you can take it out. It's the file that was called constellation chart. So basically, this one is a flat version of the round one, you know, the spherical one. Flat version of that. So where is the celestial equator on this one? This one right here. Celestial, you see where it says 0 degrees? Celestial equator. Where's the north celestial pole? Remember, that's the point above the Earth's equator, above the Earth's north pole. Well, can you show the celestial north pole on the flat map? Can you show the Earth's north pole on the flat map of the Earth? No, because you're taking a sphere, flattening it out. You can't really show the north pole that well, you know. You can't show the south pole. So the best one you can show is the celestial equator. Can you show the ecliptic? Yeah, look at this line. I think it moved here. You see this dotted line? Dot, 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 dot. They're showing you the ecliptic. Remember what I told you? Even though it looks straight like that, when you flatten it out, what does it look like? It looks like a sine wave. So on March 21, the sun is crossing the celestial sphere, the celestial equator, on its way up. It goes, it goes, it goes, it goes. When does it reach the highest point? You see, 21, June 21st. It reaches the highest point. Then it comes back down, September 21. It reaches the celestial equator, going on its way down. And then goes, goes, goes. December 21 is the lowest point. And then it goes back. Oh, okay. It goes back. There's a little portion here that is not shown here. This keeps going. And it didn't appear on the... I have to slide it over in order for you to see. It just keeps going until you get back to the beginning. You see? That's the ecliptic right there. We're going to be doing a lot of stuff on this chart during this lecture. And then even you will be able to use this chart during the quiz for this lecture. Quiz number 2. Okay, we're going to be doing a lot of stuff on this. Okay, let's go back and then continue. And so keep that in front of you, because we're going to always be going back. The zenith is the point on the celestial sphere right above a person, wherever you are, right above you. The nadir is the point on the celestial sphere opposite to your zenith. The horizon line separates the half of the sky that you see from the half that you don't. So if you visualize a semicircular sphere, okay, and then the zenith would be the point right above you, and then the horizon would be the sky like that. Let me bring something that I can show you. This gives you a couple different little models of the celestial sphere. This, of course, the Earth is, they drew it really big, but you can see here the Earth, and then this is as the sky all around you, you see, like that. And then this one, they drew really, really small. They drew the sun in there, it's a little ball. They drew opposite of the reality. The sun is really small and the Earth is really big. This one is also similar, but also what we could do over here is could be your half of the sky that you see at any point in time. So if someone lives on the Earth's North Pole, let's say someone lives right over there, Earth's North Pole, this is the part of the sky that they're going to see, you see? Like that. So their zenith is going to be the north celestial pole, right? They look straight up, they see the celestial pole. And then their horizon line is going to be the circle. Where's their horizon line going to coincide with? You see? It's going to be the celestial equator, right? For LA, it's more like this. Our zenith is about 30 degrees above the celestial equator. Why? Because LA is 30 degrees above the Earth's equator. You see? So our zenith looks like this, and then our horizon is 90 degrees from our zenith. You see? So this is LA the way. And then as the constellations rotate, we're going to be studying which ones we can see and stuff. If someone lives on the Earth's equator, this is what the sky looks like. This is their zenith. And then their horizon is the North Pole and the South Celestial Pole. You see? So when we draw this, we can kind of visualize it like this. You see over here? I drew a line and I called it Z. This is also known as your meridian. It's the line that goes across the sky right where your zenith is, and it's right above you. Why did I draw the Z over there? That's the zenith for people who live in LA. So it depends where you live. How did I know the zenith is there? I drew it 10, 20, 30. See, if you see, this is 10 degrees, 20 degrees, 30 degrees. I made it about 34 degrees. Why did I do that? Because the LA latitude is what? 34 degrees above the Earth's equator. That's where LA is. You see? So how does that help us to know that this is the zenith? Here's how it helps. Let's say you're trying to find the star called Castor. How would you find the star called Castor? How would you find the star called Castor? Isn't it near your zenith? So just look straight up. You see? Look straight up. Now, is it always going to be straight above you? No, it's going to rise during the course of a day, and then at a particular time, it's going to be right at the point above you, and then it's going to go like this. If, in this room, which way is north? That side is north? That side is north. Okay, so that's north, south, east, west, right? So the stars are going to go this way. So if I want to find Castor, it's going to rise over here. Now, when is it going to rise? That depends on the month and the what month of the year it is and everything. So let's say it rises right now. 6 hours later, it's going to be there, right above me. And then it's going to go. 12 hours later, it's going to set. 18 hours, 24 hours, and then back. Okay? You see? So that's how I would find Castor. Now, where's your horizon line? Well, as you can see again here, horizon line is how many degrees from your zenith? Like that, like that. That's 90 degrees, you see? But of course, it's not a line, it's an arc. But when you draw the arc, on a flat map, it turns into a line, you see? So you see here, I did here, H. How did I know where to put the horizon line? I have to make it 90 degrees from your zenith. So if your zenith is 34 degrees above the zero, how many degrees does this have to go down? 34, it's got to be 90, right? So I calculated it, it came out 56. 56 plus 34 is what? 10, 1, 6, 90. You see? So that's our horizon line for people in LA. In reality, this is our southern horizon line. Remember, this one is like this. You see, this one like that. Then it goes up northern horizon line, you see. So this is a little not as good as this. The round one is the better version, okay? But this is as good as you can do it on a flat map. So you can draw a southern horizon line, and then 90 degrees up this way, 90 degrees this way, and then that will take you off the chart. And then you could draw a northern horizon line, like that. But it's kind of off the chart like that. Okay, so let's go back here. Go back to the notes here. The zodiac. The zodiac is the strip of space about 7 degrees above and below the ecliptic. All the planets except for Pluto. Well, of course, Pluto is now demoted to a dwarf planet. Now, you remember at the beginning I told you, I will tell you one of the reasons, several reasons why it's demoted. One, we saw that it's really far. It's very small. It looks more like an asteroid type object. This is one of another good reason why it's demoted. It's not, the Pluto is not always found in the zodiac. Sometimes it's out above the zodiac, sometimes it's below. All the other planets were always found in the zodiac. So that's why one of the reasons Pluto got demoted, okay? So where's the zodiac here? So roughly about 7 degrees up, 7 degrees down. You can shade it. So ecliptic, 7 degrees up, 7 degrees down. Go shade, 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 shade. You see that? That means the planets are always there. Now, what does that practically mean, that the planets are always in the zodiac? Here's what it means. If the sun is taking a path like this, so where's the sun going to be roughly today? Let's just ballpark it. Today is what day? Today is February 10th, right? 11th. So that means the sun is starting to go up, 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 but it's still below the celestial equator, right? So where are we? our zenith is way up here. So the sun is way below our zenith. So let's look here. If that's north over there, this is my zenith line, my meridian. I have to look down. I have to look down. And the sun is somewhere over there. You see? Way below my zenith. It's right here. So I look straight up. I look down. And the sun is making an arc like that. The sun will rise, go, 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 set. And the next day, same thing. Next day, same thing. Throughout the days, as the days go past, it's going to get closer to me. You see? It gets closer, closer, closer. Closer, closer, closer. When March comes, it's 23 degrees from me. You see? So when March comes, it's 23 degrees below me. As the days go by, June comes. How many degrees below me is it? 34, 23, 11 degrees. So on June 21st, the sun is only 10, 11 degrees below you. Is the sun ever exactly on top of you in LA? No. Look here. You see this? The sun is never above you, directly above you. It's always going to be a little bit below your zenith, you see? What does that mean? Well, one thing it means is that in LA, you will always cast a little bit of a shadow. The sun is never directly over you. If you go down and live maybe in Mexico or Central America, there's going to be a certain day where you have no shadow. You know, the sun will be right directly over you. You cast no shadow, you see? But in LA, we always will cast a shadow. You see? So then, go back to what I was trying to say about the zodiac. So let's say this is what the sun is doing now, right? That means tonight, when I try to look for the planets, where should I look for them? When I go out to try to look for planets, I should look for them near where the sun was during the day. 7 degrees down, 7 degrees above. As the days go by, where should I look for them? A little bit up, a little bit up, a little bit up, a little bit up. By the time summer comes, they're going to be like this, you see? Like that. So can I ever look for a planet over there? Way over there? No. They're always going to be near where the sun was. So that's how you can fake your friends, is at night say, oh, over there, that's one of the planets, Venus or Mars. And they'll be saying, oh, great, how do you know? Well, I'm just joking you know. So the planets will always be near the sun's position, where the sun's arc was. You see? So that's what it means to say the planets are always in the zodiac. They're always close to where the sun is during the day in that arc that the sun is making, in the ecliptic. What should be your next question? Oh, by the way, here is a good picture of here's one way to visualize the zodiac. You see? A strip of space around the sun. You see? So it's like taking a strip like this. The sun's path is right going through the middle. You see? Now you might be asking, why are the planets close to the sun? Why are they always in the zodiac? Now we know what it means that they are in the zodiac. Why? Anyone know why? Why are they always near where the sun is? This part of the notes explains why. Let's look at a picture first, then talk about what this means. Let's look at figure 7.2. Okay, don't look at the top one for now. Ignore that. Let's focus on the bottom. What is this picture showing you? It's showing you at what the orbit of the planets would look like if you were in the outside of the solar system looking in, right? So this is Earth's orbit around the sun. Venus's orbit around the sun is the yellow one. Okay, I can make this bigger. See, this is Earth's orbit. This is Venus's orbit. Mercury's orbit is a little bit tilted, right? By how much? 7 degrees. That's why the Zenith, the Zodiac is 7 degrees thick. Venus is a little bit tilted, you see. And then the next one, going out, Jupiter, Neptune, Uranus, Neptune. Look at Pluto. Okay? You see that? So therefore, Pluto is not always going to be in the Zodiac. So how does this explain that planets are always near the Zodiac? Well, notice that the solar system more or less looks like a flat sheet, like a pizza, you know. So if the Earth is here, and if I need to look at the sun, I got to look this way, right? So in the evening, if I want to see Mars, which way do I look? The opposite way. So if I'm looking at the sun this way, the opposite way, the Mars. So basically what that means is the Mars and the sun are kind of lined up, you see? And also the other planets, they're all on a sheet. What if the solar system looked like this? Like Mars was doing this, and then Venus was doing that, you know? Then where would they be in the sky over here on the celestial sphere? Let's say Mars was doing something crazy like this. Then how could I ever find Mars here? Well, depending on the time of the day and the month of the year, Mars could have been here. You see? It could be all the way down here. It could be here. It could be here. But because Mars and all the other planets are mostly flat with the Earth's orbit, that means they're more or less going to be only here. You see? Wherever the sun is doing, the planets will also be doing the same thing. They're going to be in that space. So here, 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 here. They're never going to be all the way up here. They're never going to be all the way down there. And that's why. That's the reason why. But you see Pluto? It's not true. Pluto might be all the way up here, all the way down here. So it might be off more. So again, you can see Pluto is different. Okay, so now we can see here the inclination of the orbits of planets. Mercury's orbit, 7 degrees. Venus, 3.39. Earth, 0 degrees. Why? By definition. Earth's orbit is the one that we're comparing everything to. Uranus, 0.77. So if I were to ask you on the quiz or the test, which planet's orbit is closest to the ecliptic? Which planet will always be found the closest to the sun's path? You're going to say Uranus. Why? Because the Uranus's orbital tilt is the smallest. And therefore, it's always closest to the ecliptic. So Uranus is 0.77. Which one is the farthest? Mercury. It's tilted by 7. So it could be, that means Mercury could be on the edge of the zodiac. Way at the edges, the top or the bottom, or it could also be in the middle. But the one that could be the most off from the ecliptic is Mercury. But then Pluto is even worse than that, but Pluto is now a dwarf planet anyway, right? Okay, now we're ready to talk about positions of stars on the celestial sphere.